Hello, and welcome back to the course on classical electromagnetism. So before we start this lesson, let us first review some concepts. So in the previous chapters or lessons, we have discussed about polarization. So it's basically just a description of the change in dipole moment over the change in volume. We also have discussed about bound charges. So if an object is polarized, there could be bound charges. There could be surface bound charges and volume bound charges, where the volume bound charges is just the divergence of the polarization. And we also have discussed about the potential of a polarized object. So it's due to, the first term is due to the surface bound charges, and the second term is due to the volume bound charges. But it's not always, the volume and the surface bound charges are always not present, not necessarily present at the same time. There are times when there are only surface bound charges, but there are times that there are both present, the surface and volume bound charges. So for this lesson, we will be discussing about the field of magnetized objects. So you will expect familiar forms of the field, the bound charges, and in this case, we will have bound currents. So in the same manner as polarization is electric dipole moment per unit volume, magnetization is just magnetic dipole moment per unit volume. So if you have a material, note that material is composed of atoms, and atoms have electrons looping around the atom. So basically, you have tiny current loops, and these tiny current loops create magnetic dipole moments within the atom. So your material's individual tiny current loops or magnetic dipole moments are actually randomly oriented. Now, if you exert or if you expose this material to an external magnetic field, in a similar manner, when you expose a material to an electric field, this magnetic field will actually try to will act a force on the dipole moments, and aside from that, they will also act a torque. So the magnetic field or the magnetic dipole moments will actually try to align with the magnetic field if you have ferromagnets or paramagnets. But if you have diamagnets, the magnetic dipole moments will actually disalign with the external magnetic field. So this material is now what we call magnetized. So when most of its dipole moment align or disalign, in the case of diamagnets, with an external magnetic field, then the material is said to be magnetized. So what is now the field of a magnetized object? So it's all related in the same manner with for polarized object. We try to find the electric potential first. So in a similar manner, you can get the magnetic vector potential of a magnetized object. And knowing the vector potential, you can now get the magnetic field. So the magnetic field is just the curl of the magnetic vector potential. You can also write the magnetic vector potential in terms of the bound currents. So in the same manner, where a polarized object has bound charges, surface bound charges, and volume bound charges, a magnetized object also has surface bound currents and volume bound currents. So it's the first term in the potential here is the potential due to the surface bound currents. The second term is due to the volume bound currents. So Kb is the surface bound current density. It's just the cross product of the magnetization and the n hat, the unit vector perpendicular to the surface, and JB here is the volume bound current density, and this is just the curl of the magnetization. But again, if your magnetization doesn't have a curl, then there will be no volume bound currents. So if you have a material and you magnetize the material, so there will be volume bound currents within the volume of the material, and there will be surface bound currents within the surface of the material. But I would like to emphasize that these macroscopic bound currents, the surface bound currents and the volume bound currents, are actually due to microscopic current loops within that atom. So current is created as a net effect or a net combination of all the current loops within the constituent atoms of your material. That one. So that is created by the current loops of your atoms. Okay. So let's go directly to an example. So for the first example, find the field of a uniformly magnetized sphere. So we have actually solved this problem over and over again. So this problem is just equivalent to a spinning shell of charge. Take note that if magnetization is uniform, therefore it will have no curl. So del cross M is 0, meaning there will be no volume bound currents. No volume bound currents, and only surface bound currents are present. So in this case, the surface bound currents are actually in the phi hat direction. This is the surface bound currents, KB. Oh, I should have chosen a brighter color. Okay. So only surface bound currents at the surface. So basically, it's a spinning shell of charge. So it's a shell. It's not a solid. So it's a shell of charge. So we have actually solved this problem before. So the vector potential inside is just proportional to the surface bound current density, KB, which is just M cross R hat. And in this case, M cross R hat is M sine theta P hat. And outside, when R is greater than or equal to the radius, capital R, you get this value for the magnetic vector potential. And you take the curl of this in spherical coordinates, and you will get the magnetic field inside is just 2/3 mu naught M. So it's directly proportional to the magnetization. So the magnetic field is in the same direction as the magnetization. So you have to take note that the magnetization is perpendicular always to the vector potential and the surface bound current density, and they obey the right hand rule. So if the magnetization is in this direction, this is the direction of the surface bound current density, and the direction of the magnetization inside is also the same direction as the magnetic field inside. So the magnetic field inside and the magnetization have the same direction inside the sphere. Outside the sphere, if you take the curl of this in spherical coordinates, you will get the magnetic field of a dipole. But now it's in terms of the magnetization M instead of the magnetic dipole moment small m. So this is the magnetic field of a dipole in terms of the magnetization M. So its magnetic field will somewhat look like this. Outside, it's a dipole. So it will curl around just like the Earth. So it's a dipole. Okay. So in this second example, we are asked to find the magnetic field of an infinitely long, uniformly magnetized cylinder. Again, in this example, there is uniform magnetization, meaning there are no volume-bound currents. And in this case, if the magnetization is parallel to the axis of the cylinder, then by virtue of right-hand rule, the magnetic surface bound currents are in this direction. So it's in the phi hat, direction. Okay. So again, in this case, there are no volume bound currents because there's no curl for the magnetization, because the magnetization is constant or uniform. But for the surface bound currents, it's just m cross n hat. In this case, n hat is the direction perpendicular to the surface, and this is the s hat direction. So basically m cross n hat. So m, our magnetization, m is actually, if it's uniform, then it has a magnitude of m and direction of, say, z hat, mz hat. So you have z hat cross s hat, and you will get a phi hat. So basically this is m phi hat. So its magnitude is the same magnitude as the magnetization, but its direction for the surface bound currents is phi hat. Okay. So the easiest way to solve this problem is actually to use Ampere's law. So you will have closed integral of, say, for the magnetic field inside that BL equal to mu naught I enclosed. So since our current is in the phi hat direction, our Amperian loop will be this one. We will try to see how much current is enclosed by the loop. So in this case, the current enclosed is just integral of KdL. So, but in this case, our KB, since that's our surface bound currents, is uniform, M, and integral of dl is just the total length enclosed, say, assuming this length is L, so it's just M times L. So, in this case also, the magnetic field inside is uniform at all points within our Amperian loop. So you can take it out of the integral, and integral of dl is just the total length. So mu naught I enclosed is just M times L. So magnetic field inside is just mu naught M. So the magnetic field inside is actually in the same direction as the magnetization. So inside, the magnetic field is in the same direction as the magnetization. So how about outside? So outside, if you make an Amperian loop outside, then the current enclosed is 0. So basically, the magnetic field outside is 0 because there's no current enclosed outside of our cylinder. So inside, it's mu naught times M. So you will notice that the magnetic field is actually directly proportional to the magnetization. In fact, they have the same direction. Okay. So let's now go to another example. So how about now if you have a non-uniformly magnetized cylinder, and magnetization is now along the phi direction, so phi hat. So you will expect, by virtue of right-hand rule, if this is the direction, if the curl of your fingers is the direction of magnetization, you will expect that this is the direction of your current, or your surface current density or volume current. So the current will be along the axis. So the current I will be along this axis, the perpendicular. Okay. So first, we need to find the bound currents. So of course, there will be surface bound currents. So M cross N hat. So in this case, our magnetization at the surface. So at the surface, the value of M at the surface of the cylinder, take to this, the magnetization depends on S. And the surface of the cylinder is at S is equal to R. So basically this M is K R squared phi hat. Cross it with N hat. In this case, N hat is S hat. So phi cross S, that will actually give you negative Z. So you will have K R squared negative z hat or negative kr squared z hat. So that is the surface bound current density. Take note, it's capital R here because we are at the surface. The surface is at S is equal to capital R. Now, for the volume bound currents, so we have JB. It's the curl of the magnetization. So if you take the curl in spherical coordinates, you will only one term will survive. The term 1 over S partial with respect to S, S times the phi component. Since our M magnetization only has a phi component, it doesn't have an S component, it doesn't have a Z component. So the phi component is actually K S squared. Z hat. So only this term in the curl will survive. Okay. So taking the derivative of this, and you will get the volume bound current density is 3Ks Z hat. So we now have the surface bound current density and the volume bound current density. Okay. So there are volume bound currents inside. There are also surface bound currents at the surface. Okay. So let's now try to find the magnetic field. So it's still easier to use Ampere's law. So for the magnetic field inside, so we have the magnetic field inside dot dl is equal to mu naught current enclosed. So what we will do is we will make an Amperian. Since our current is along the axis of the cylinder, then our Amperian loop in this case will be circular, enclosing our loop or our currents. So our Amperian loop is a circle with radius S. So that is our Amperian loop. So it will be just reduce to magnetic field inside times the length of our Amperian loop, that is a circle. So the total length of the circle, perimeter of a circle, is 2 pi s. Then the current enclosed. In this case, the current enclosed, this is just within the volume, so it's just integral of J dA or J dot dA. So J is 3Ks, dA is S ds d phi. So this is a surface integral. So integrating this, you get the current enclosed is equal to 2 pi k s cube. So 2 pi k s cube. So this is the current enclosed. So this is 2 pi k s cube. So the magnetic field inside will just be, so 2 pi will cancel out. We'll get mu naught ks squared ks squared. So the direction of the magnetic field inside is in the same direction as M. It's phi hat. So basically this is phi hat. It's the magnetic field inside. But ks squared phi hat is actually the magnetization. So again, we still get a similar result as in with the previous problem. So it's mu naught M. So the magnetic field inside is still mu naught M. Okay. So that's the magnetic field inside. So for the magnetic field outside, we do the same. So the magnetic field B outside the dl, the mu naught I enclosed. In this case, I enclosed will be, since your Amperian loop outside will now be very large loop, and it will now include the surface bound currents and the volume bound currents. So basically it's JDA plus KDL. So JDA plus KDL. So you will have J is again 3K integral of S squared. You have SDS dP. And then, of course, this is surface integral. Plus K, it's actually negative KR squared. Negative KR squared Z hat. So its magnitude is just negative KR squared. So it's uniform. So DL. So basically just our DL, sorry. Our DL in this case is actually RD theta. RDP. This is from 0 to 2 pi. This is our DL. Our DL is RDP. So of course, the total enclosed is actually 0. Why? Because the volume bound currents and the surface bound currents will actually something like cancel each other out. The current enclosed is 0 and the magnetic field outside is still 0. Okay, so that is it. So that is the last example, and that is the end of this lesson. So in the next lesson, in the same manner of progression, we will discuss about electric fields in matter. We will introduce the equivalent of electric displacement, and in magnetism we call that as the auxiliary field. So I will see you again in the next lesson.